Okay, so last time, what were we talking about?
Atomic structure and spectra.
Yep, atomic structure. We started looking at the H atom, specifically where we're breaking apart the Hamiltonian of the H atom. H hat, and H hat can always be broken into what two contributions?
Kinetic energy and potential energy.
Kinetic and potential. And then we were delving into what are the attractive forces in an atom, what parts go into the kinetic energy part, what parts go into the potential energy part. And we were discussing it for an H atom, right? We had already arrived at what V looked like. We said V depended on R. What was the value of that? Or what was the equation for it?
Negative Z times E squared divided by 4 pi epsilon R.
Yep. And what is this? Like, what does this part describe?
Permittivity of free space.
It's the
That's what that epsilon does.
All right, you're talking about the whole thing?
Yeah, like
Coulombic potential.
Yep, it's the Coulombic potential, and so this is the Coulombic potential. And what's it describing though? Like what interaction?
The electron to nucleus forces.
Yep. Okay, so we talked about the potential energy part. We discussed why is there a negative sign here? Why is that negative sign there?
It's something that decreases the overall energy.
Right. So it decreases overall energy. That's all we really have to worry about for the potential energy. Let's talk about the kinetic energy. So returning K hat. Okay, so what's going to contribute to the kinetic energy? We described 3 forces that are going on in here.
It's the charge of the electron and the charge of the nucleus.
I'm sorry, can you repeat that again, Josh? I couldn't hear you.
Charge of the electron and charge of the nucleus.
Not the charges, but
the speeds, I guess.
Yeah,
or not
the
movement.
motion, the kinetic energy of those guys. So we got to worry about the kinetic energy of the electron, and we got to worry about the kinetic energy of the nucleus. Because remember, we're talking about the H atom. There's only an electron and a proton. Okay. What's the kinetic energy of the electron going to be equal to? Or what do we always have?
Mass times something by velocity.
We could do that.
Squared.
What do we typically do in quantum? Like, what's that expression we always come up with for a kinetic energy?
Is it px or py? That like
it's related. Yep. Yep.
Woo.
Josh, you're right. It is related to momentum. 2m, and what else do we need here?
D over
Px. First derivative, second derivative.
Okay. Is that good enough for an atom? How many dimensions does an atom exist in?
3.
3. So what else do we need?
The derivative in the y.
Oh, plus d
max.
dxy squared.
Yep. And finally, ez, right? Okay, there's another way we represented this. You remember how we represented that? To make a shorthand way?
Curl symbol.
Yeah.
Upside down triangle.
Yeah, upside down triangle. And we're going to put sub E there. This is known as a
H bar or
gradient.
H bar squared?
That's, oh, it should be H bar squared, I'm sorry. There we go, that matches it. Got excited about this part. So this is called the gradient. What's it gonna, we're missing one more thing here. What should we change that mass to?
I.
Not I.
Mu.
All the rest
Nope.
mass.
Oh, that little Mewy thing.
No.
Nope, because that's for a two-body system.
ME.
Yep, mass of electron. That's all.
Oh,
Okay. Now, the nucleus part. What's that going to look like?
The same thing, but mass of a nucleus.
Yeah, pretty much.
Doctor?
Was that a doctor from like Little Shop of Horror?
No, it's just I'm a doctor.
Oh. No, I meant the way you said doctor. Reminded me of that
No, it's just natural.
one. Okay, now let's combine all of our stuff into one Hamiltonian. KE, the kinetic energy of the nucleus, and then that potential. So our Hamiltonian looks like negative h bar over 2, mass of electron, delta E of our electron, minus h bar squared over 2m nucleus, gradient of the nucleus squared, minus z e squared 4 pi epsilon r. Okay, we can simplify this though with something you guys were talking about a bit earlier, like just a moment ago, that had to deal with these masses. What could we do?
Combine them together and make mu. Because we're looking
Combine
at
them
two
together for
atoms,
mu.
electron and nucleus.
2m delta minus z e squared epsilon naught r. Why does that benefit us?
To be simpler.
Yeah,
whoa. Wait, we can just do that.
Yeah.
Everything just kind of combines. All right.
yeah, we can smack it together that way. So that's what the Hamiltonian looks like. Okay. Now, what about the wave functions? We always consider the wave functions. So we're going to talk about that in a moment, but to explain what we're going to do, we have to talk about the potential for a moment. So thanks to the potential, only depending on R. That distance and it's centriosymmetric. We can separate the wave function. We can separate it into a part that depends on the angular part and the radial part. So a part that depends on R and another part that depends on theta and phi. So the wave function can be separated into an angular part YL M sub L, like we've seen before. That's our our angular part. And that depends on theta and phi and the radial part. And we're going to express the radial part as capital R, which depends on that radius, how far away the electron is from the nucleus. So if we were to represent this mathematically, we would have our wave function. And what does the wave function of a hydrogen atom depend on? What are the the independent variables. Well, what things matter when we're talking about the electron itself?
The charge.
It's
Charge,
energy
that
level,
matters.
so
That's a
it's quantum
constant,
number.
though. What were you saying, Josh?
It's energy level, so N.
I couldn't hear you again. I'm sorry.
My microphone sucks. N. Like it's
And
energy level.
oh, the quantum numbers. Yes, that will change the look of the wave function, but that's still sort of like a constant in a way. So what things are going to be changing?
The distance between the nucleus and the electron.
Yep, and we gave that the symbol R. So that's the distance. What other things do we have?
Theta and phi.
Theta, yep. And phi. So our wave function depends on these three things. But what we're saying is we can split this up into two expressions. We have a part that just depends on R, and then we have our spherical harmonic function, which we've seen in the past. Okay, so we're going to explain what these R values are in a little bit. Why? We've seen this before, right? We needed to know L and we needed to know ML. Okay. Any questions so far? Okay. What we're going to ask now is, we're going to ask, can the Schrodinger equation actually be separated? So can we put this into separable, solvable expressions, because we have R and we have Y. And we have we multiply these two wave functions together and we get the resulting wave function, the one that actually describes how our electrons behave. So can we split the Schrodinger equation apart? In the Schrodinger equation, for this system, be separated. Okay. So what's the basic form of the Schrodinger equation again?
H wave function equals E wave function.
Yep. We solved for what that Hamiltonian was in this system. We have negative h bar squared over 2 mu gradient psi. Then we had that potential psi is equal to E psi. But we said psi was made up of two functions. We said psi is made up of R and Y, right? For the next bit, what we're going to do is we're going to make this a little bit easier. We know capital R depends on little r, and Y is this stuff. We're going to simplify it to look like this. Okay? So that way we don't have to keep writing this part out and that part out. Is everyone comfortable with that? Yeah, I hear no major complaints, so let's go with it.
Yeah, I'm scared. It scares me when we do.
Don't worry, it'll get better. Maybe. It's going to look really bad, and then it's going to look really good.
If you're honest.
Yeah. Don't worry, once we move up to even more electrons and more like nuclei, then it gets weaker. And then we have our Y plus V R Y is equal to E R Y. Okay. We now have an expression for this guy that we stated way back about 3 lectures ago. So let's plug in for this part. You may remember that gradient in spherical polar coordinates was this big, long, complicated thing. Oops, this should actually be a 2r er. Okay. You remember what this thing was?
Um,
I don't have to look back at it. I can't remember what the expression was. I know what it depends on.
Was it 1 over sine something times the second derivative of that plus 1 over sine?
it's the theta and phi like
Yeah. It's
whole equation.
theta. You don't have to write this down, but just know that this is what this thing is. Oops, covering it up. I much more prefer to write that symbol than this whole stupid thing up. Okay? So everybody sort of remember that. Okay, then we have ry plus v ry is equal to e ry. Okay, what can we do next?
And you just divide by ry.
You could, but then you get this complicated expression through.
Well, if you know that r is dependent on the r terms. can
Yep,
you,
so
like,
r depends, so this guy, what's it depend on?
on the r related terms, so r.
Right, so what parts of this are these differentials going to influence?
So the first 3 terms are influenced by r.
Right, so these guys, right?
Yeah, I guess just those ones. Yeah.
What about y? What does that depend on again?
Just the
First
last
term.
term. So that one's
Mhm.
phi and psi
Right.
or theta.
So we can apply those portions of this wave function to the parts that the derivatives depend on. So we get negative h bar squared to mu. Whoa, what a focus. What's this first term gonna become if I distribute these 2 functions through? So this first one acting
So it
on
becomes d squared over dr squared. So it's the first 2 terms times r plus the second term, or plus the third term times y.
Well, remember, we're distributing it all the way through, so y times the second derivative of big R with respect to little r, plus what's going to come next. And remember, this is a 2, not a differential. So what's going to come next?
Would it be 2y over r d over dr?
Yep. The last term? So this bit right here, what's that going to become?
R over r squared. Y, yeah, I guess. I don't know how we would write that in.
Yeah, this one was lambda y.
Lambda y, okay.
Yep. And what we're going to show, this parenthesis means it's at lambda y, or lambda is acting on y. Because remember, order matters. Oh, except I'm sorry, I should have highlighted these. Make it a little bit more clear. Plus V RY is equal to E RY. Okay, but now we want to try to separate these variables out, right? So if you look, y is in this first expression still, it's in this second expression, and r is in this third expression. What would you do, or what would you multiply by to isolate like this term to be just dependent on r, and this term to be just dependent on r, and this one to be just dependent on y? Or what have we done in the past? So there's something we want to multiply by. What would you multiply this by to get rid of that y?
1 over y.
Yeah, 1 over y. Same thing with this guy, right? What about this r? What would you multiply that by to get rid of that r?
1 over r.
Yeah, 1 over r. So we have to have some common term to multiply all of these things by.
R over y?
R, actually, oh, ry. And we're going to throw in an r squared there just to get rid of that r squared, because we want this term just completely dependent on the angular momentum part. So if we multiply by r squared over ry, let's see what we get. So we still have that negative h bar squared over 2 mu. If we multiply this first term by r squared or divided by ry, what is this going to become?
R squared over r times d squared r dr squared. Is my microphone super bad?
No, it's good.
I laughed because he paused.
Yeah, he's rethinking everything right now.
Yeah, I am. I'm stuck. I'm looking at something and my math isn't working out how I want it to.
Yeah. How is that like just okay that we end up with an r out front?
Oh, that's okay. We're just multiplying
okay,
by
'cause
some factor.
Uh,
But I'm messing something up. Staring at it for a second. We'll just do it. All right. And we'll see where I messed up afterwards.
Great.
Yeah, you guys like that, right?
oh yeah.
Second term, what's that going to become?
Two r squared r, never mind, 2r divide y,
Yep.
or not y, no,
2r
divided by
what?
like capital R.
Yeah. d plus this last term.
1 over y, lambda y. Lambda squared y.
Okay, we'll highlight the functions in red. Okay, now we have to do that to all parts of this function, right? So what does the potential part become?
V r squared.
Yep, v r squared, and the energy portion.
Er squared.
Yep. Okay, so we've done this before. Like if we look, these are almost like the same thing as a 3D particle in a box, or in our case, like when we were looking at a particle in on a sphere, we've looked at these types of expressions before and solved them. Now, this term, what's it only depend on? That first one.
R,
Yep, second one.
just R,
Third one.
Y.
Y,
Y. Yep. So this section depends only on R. This section depends only on Y.
Good Quizlet question.
So the question
I got
was,
jokes.
well, I'm sorry, what'd you say, Tara?
I said it's a good Quizlet question.
Oh yeah, it is. You might see it in your near future.
Fire and power.
You might, maybe, I don't know. Okay. So we already have a solution for one of these. Which of these do we have a solution for? Oh, and before we do that, so therefore these are separable. Okay, but we have to talk about their solutions. So this portion along here, we have a solution for the theta. Actually, so this depends on R, this guy depends on theta. So we have a solution for the part that depends on theta and phi. And if you look back at our notes, it was negative L plus 1, and we get Y back out. Okay, therefore, if we're looking at this portion, 2 mu, we got Y down here. Y. We have a portion that can solve for this, so we get negative h bar squared 2 mu y times negative L times L plus 1 times y. Can you simplify this expression for me? Or can you tell me something that cancels out?
Y's.
Yep, y's go away. Good. Anything else going to go away?
Y's on the other side.
Oh, over here, yeah, they can go. They can actually go. Well, this has to act on that guy first. So we're going to ignore that part. Anything else over here?
The L's.
Nope, L's hang around. All I'm looking
Oh,
for is
negative.
yeah, negatives. Negatives go away. So what's our overall expression?
H bar squared over 2 weird letter and then
Yep,
negative
mu.
L plus 1 Y.
Yeah.
Y's gone.
So there we go. So what we're going to do is we're going to plug this back into our Schrodinger equation. Plug back into Schrodinger equation. So back into this guy up here. So if we do that,
Can you put it down just a little bit? I gotta get.
Yep.
Yeah,
Yep,
right
like
there.
there?
I just had to get the therefore line.
so we get negative h bar squared over 2 mu times r er squared plus 2 r dr. Oh, we're forgetting to divide by r here. Plus vr squared plus h bar squared L times L plus 1 divided by 2 mu is equal to E R squared. Okay. So what do you notice about these two portions here? Or this thing? What does that angular momentum part only depend on?
U.
Yeah, it depends on that rest mass. What else?
Momentum quantum number.
Yeah, the angular momentum quantum number. So whatever orbital we're talking about, that's going to influence this part. We call this the effective potential. So we're going to combine all of these things together into one potential, Z effective. And we say that's equal to negative Z E squared 4 pi epsilon naught R plus L times L plus 1 H bar squared over 2 mu.
So those R's don't cancel
The R's
for
don't-
the first part, because that's like what B equals to. Shouldn't be multiplied by R squared.
yes, there is an R squared. Oh, so like where does that R squared go?
Mhm.
Good question.
Wouldn't that cancel the bottom?
There should be an R here also. So where does that come into play? Not too sure.
It'll be like that.
Yeah, it comes apart somewhere. Not too sure where.
Just simply because like what that v was equal to, like what we stated previously,
Yeah.
was what we have on the page right now. But then I would figure that thing should be multiplied by r squared, which would cancel the bottom r and put an r at the
Oh
top.
yeah. Yep. Nope. It doesn't cancel that r squared. There are reasons for that, which I will explain next class on how this comes about. But when you look at these expressions together, that's the result.
So that's the simplified version.
This is what they call the effective potential. So we've
Okay.
basically combined these two things to express this.
Okay. And it just happens to end up looking like that.
Yep.
All right.
Yep. Okay. So we're almost to the end. So the known solution. With this, with this differential equation, mathematicians have actually worked out previously. So are associated, they are the associated. Langure, that's how you say it, polynomials that are restricted based upon two numbers. Restricted. Based on two numbers. And those are the first two quantum numbers, n and L. And must satisfy the criteria. What's the relationship between n and L have to be?
-1.
Yep. L has to be n minus 1 or 2, 0, right? So n has to be greater than L. Okay, so now we have the following resulting restrictions. The resulting, the results. There we go. The results the results result in, geez, I'm not going to write that. All right. The restrictions. Sorry, trying to make language work in my head. It doesn't work. For the hydrogenic wave functions. We have the radial part, where n must be greater than L, and we have the angular part. And in that angular part, the absolute value of ml must be less than or equal to L. So those are the things that we found so far. Okay. In the resulting wave functions, we'll talk about what they are next time, but I'm going to post them online for you. The way that they look, which will scramble down in the future, are these. These are their results. So what these rows are, row is related to R and a value of n, but these are the resulting wave functions. So all we've done is we slap the radial part. So we have the radial component, and then we have the angular momentum component, that y that we have to look at. Okay? All right, so next time, what we're going to do, we're going to go into some mathematics behind this stuff. We're going to show that the Bohr model of the atom didn't do that bad of a job. When we look at the most probable spot that an electron will be in the hydrogen atom, and we'll see some crazy math. So
that says the absolute value of ML is less than L, right? Less than or equal
yes,
to that?
is less than or equal to the value of L.
All right.
Okay. Are there any questions about the material that we covered so far? Okay.